Okay, good afternoon, everyone. We are very happy today to have Rob Myers from Perimeter, and he will tell us about his interesting work together with some amazing people on complexity equals anything square, or complexity equals the square of anything. So please, Rob, take it away.
Okay, thank you. So as Hugo said, this is I'm going to be reporting on this work that I did with some very smart people, and it came out, and hopefully there'll be another paper in the not too distant future, and I'll tell you a little bit about some new things that are going to appear there. In any event, let's see if we can move the slides. There we go. Here is one of my favorite slides of all time. Holographic entanglement entropy was a brilliant insight now, I guess 15 years ago, by our friends Ru and Takinagi, who realized that you could turn a calculation of entanglement entropy and the boundary theory into a geometric calculation about extremal surfaces in the bulk of ADS. And as I say at the bottom of the slide, this really became a fruitful forum for learning about both sides of the ADS-CFT duality. We learned new things about quantum field theory, but at the same time, we learned new lessons about gravity, or in particular, how quantum gravity organizes itself. And it gave rise to a slogan that said space-time equals entanglement. And it just captured the idea that we realized that entanglement of the quantum degrees of freedom was an important aspect in the emergence of the bulk space-time. So it was a little bit disheartening when Lenny came along a number of years ago now, with the title "Entanglement is Not Enough." What he really meant, as I indicated, or as indicate here, is entanglement entropy is not enough. So entanglement entropy is sort of one diagnostic of entanglement. And what Lenny was pointing out is, well, we should pay attention to other potential diagnostics of entanglement and to get a fuller picture of the ADS-CFT and how that works. In particular, he was interested in understanding the physics or the geometry of our holographic space-time behind black hole horizons. And so, as my picture indicates here, we all know, thanks to the beautiful work of the EHT collaboration, what a black hole looks like. But as usual in a talk like this, instead, you're going to get stick figures or sketchy diagrams like this to represent our black holes. And just a quick reminder, you know, my eternal black hole, which I'll be looking at time and time again in this talk, is dual to a Thermofield double state. So I have two copies of the CFT corresponding to both boundaries, and they're entangled in this state here. And so we're going to be using that in the discussion. Now, to understand Lenny's slogan or title, we can think about an experiment or a thought experiment done by Hartman and Maldacena several years before. And what they thought about was the following. So this green picture is a time slice running through across the T=0 slice, or the Einstein-Rosen bridge of my ADS black hole. And they're going to evaluate the entanglement entropy, but the problem they chose is one where I choose a region or a set of degrees of freedom in one of the boundary CFTs, and I jointly consider that with a corresponding or a reflected set of degrees of freedom here in the opposite boundary or in the opposite CFT. And then if you ask or you apply the usual Ru Takinagi prescription and ask what is the entanglement entropy, you find, at least when these regions are big enough, that the Ru Takinagi surface actually stretches all the way across the Einstein-Rosen bridge in these two components, as I've illustrated here, or the blue line that goes across there. And so it really, the Rutaki-Nagy surface feels or probes, if you like, that entire time slice. Now, as I push the time forward, I'm pushing it forward on both sides. For a while, the surface stretches and the time slice, or it starts to probe this region just behind the black horizon, close to the bifurcation surface. But very quickly, if I continue pushing my time slice forward, what I find is that the Rutaki-Nagy surfaces snap back so that the two components now are, well, these blue lines were sketched out here so that they each live on either side of the black hole horizon, or they each have, there are two components in the two asymptotic regions of my black hole. And that's something that had to happen. It's enforced by an inequality in quantum information called subadditivity. It says that the entanglement entropy, the joint of these two regions considered jointly, can't be greater than the sum of the entanglement regions of the two individual regions. And these two surfaces are, in fact, the RT surfaces for the individual regions. And so what we're doing in this configuration is we're actually saturating this inequality. And so very quickly what happens is you reach this saturation point, and that's what's happening, that the entanglement entropy can't increase any further. And of course, it remains a constant as we push forward. One of the things that Lenny thought about or discussed in thinking about this is that if we think about entanglement entropy, it's a function, as I've shown here, or a functional of the eigenvalues of the reduced density matrix. And what he thought is that, well, we need a probe of the system that is more sensitive. In particular, it should be sensitive to the phases, perhaps, that are coming into the state as we evolve it forward in time. And his suggestion, of course, was we should think about complexity in this holographic context. So I'll take a pause and, this may not be familiar to all of the audience, so I'll take a moment just to explain a little bit about what complexity is. And it's really, something that's studied by computer scientists or quantum information theorists, but it is what our intuitive sense of the word complexity is, which is how difficult is it to implement a task? And for us, the question will be, how difficult is it to prepare a particular quantum state? And we're going to do that using a particular approach known as a quantum circuit model. And so in this case, what we're doing is we're starting with a very simple reference state. Of course, simple is in the eye of the beholder. And so for us, what that means is typically we think that it's an unentangled state. So we have a certain set of degrees of freedom, and we imagine that we have a state that's unentangled. So if I had a string of spins, I could just pick them all to be individually in the spin down state. Then what I want to do is I have a particular state of interest, and I want to build the unitary then that transforms my reference state into this target state, but I'm going to do it in a very particular way. I'm going to write down a certain set of simple gates that only act on a few degrees of freedom at a time, or a limited number of these spins at a time. And then I'm going to join them together and build a circuit as it is shown here, that's going to transform my reference state into the target state. And so I think about all the different ways I can do that. In the case where I have discrete spins and discrete gates, I may not be able to get precisely to the state, or the state that I produce may not be precisely the target state that I was interested in. And so I may have to introduce a tolerance which means that if I get by some measure pretty close to the target state, I'll be satisfied and I'll stop I'll stop my circuit there. But given those constraints, what I do is I think about all of the possible circuits that I can build in this way, all the different ways to join together these gates, and I look for the optimal circuit or the minimum number of gates required to prepare my target state. And that number then is the number that I assign as the complexity. Now, one observation is that, this was a pretty abstract discussion or description of complexity, and I made all sorts of implicit references to choices. In particular, there was a choice of my reference state, there was a choice of the gates that go into building my circuits, and there was a choice of a tolerance. And so you might ask, is the answer that I get for the complexity going to depend on those choices? And of course, the answer is yes. Now, the computer scientists, when they approach this, they look for robust features that are independent of the details of the model or the construction that they're looking at. And so they ask questions like, is it for a large system, is the size of the circuit or the complexity polynomial or exponential in the size of the circuit? And so we're motivated to ask, well, we have to ask robust questions. We have to ask or try and figure out, that's actually part of the understanding of holographic complexity. What are the questions we can ask that are going to be robust and give us some new physical insight that are going to not really depend on all of the details? But as I say here in the corner, we're going to go beyond just asking whether states are polynomial or exponential in our resources. So that's just a brief introduction to complexity. I guess I could take a pause there. Most of you are probably experts, but I'll pause, take a sip of my my Coke Zero, and ask if there are any questions. Well, seeing no questions, I'll carry on. And I'll say that, as well as coming up with this idea, he came up, Lenny proposed two approaches to holographic complexity, as I've shown here. And the first is, the first is complexity equals volume. And so this was in some sense inspired by the Ryu-Takenagi construction, but we've cranked the dimension up. So what we're thinking about now is we're going to choose a time slice in the boundary theory, and then we're going to think about all possible surfaces that stretch between or fill in the bulk geometry here. So I've got my two boundary slices, and then I'm in some sense choosing a Cauchy slice that runs all the way through the bulk space-time. And what I'm instructed to do is evaluate the volume, the space-time or the volume of these codimension-one surfaces, and maximize that. And the maximal volume then, he argued, can be a measure of the complexity of the state, the boundary state on these two time slices. The next proposal was complexity equals action. There, what he was doing was looking at some region of space-time known as the Wheeler-DeWitt patch. If you like, it's the domain of dependence of this extremal volume slice or any Cauchy slice between those boundary time slices. And that defines then a region of the bulk space-time. And on that region, I'm supposed to evaluate the gravitational action. And again, Lenny's collaborators argued that that could be another way to measure the complexity of these of the state on these boundary time slices. By construction, both of these observables actually probe the interior of the black hole, as Lenny was hoping or looking for. And in fact, they probe the interior for arbitrarily late times, i.e., as I push the boundary time further and further up, I'm just probing more and more of the interior of the black hole. I'll also say that some folks in Texas, or at the time in Texas, also suggested that, well, you could look at the Wheeler-DeWitt patch, but just evaluate the space-time volume of that region of the space-time. And that seems like, or it is, a much simpler calculation, but they also argued that this could be another way to measure the complexity of the boundary state. Now, those are interesting new geometric observables in our gravitational theory, but one has to ask the question, why should I think that we're talking about complexity of the boundary state with those observables? And so there are a number of reasons, and I'll run through them very quickly. One is a connection to a particular set of tensor networks known as the multiscale entanglement renormalization ansatz, or MIRA. This gives an efficient way to represent the ground state wave function of two-dimensional critical systems, or 2D conformal field theories, if you like. But the idea is that I've got a certain circuit. This really is a quantum circuit. At each one of these blobs, there's some inputs, and they're processed by a unitary, and it spits out, well, some other answer, and I connect them in a particular way. And so that's one idea, this MIRA network. But then Brian Swingle argued or noticed that there's a hyperbolic geometry hidden in this particular construction. And so he made arguments, in particular using entanglement entropy and other ideas, that this circuit actually represents a time slice in the ADS space. Now, if I combine the idea that this is a quantum circuit with Brian's observation, then, counting the number of gates or counting the number of blobs in this picture is just giving us a measure of the volume of this time slice in ADS space. And so that looks very much like this complexity equals volume prescription over here. And so that was shown to give us then some intuitive reason to think complexity equals volume may be connected to complexity. A more quantitative one, although again a qualitative argument, is that it was observed if you look at the late time behavior, the time rate of change as I'm pushing these observables up in my on the boundaries of my space-time here, that the time rate of change is proportional to the mass at late times. And so why should that be an indication of complexity? Well, what Lenny and Adam Brown and others argued is that what I have to remember is that the boundary CFT is a system with a very large number of degrees of freedom. It's also a chaotic system, so the spectrum is very dense and random. And they argued that you should expect the growth to be linear in time. The idea being that essentially as you're evolving the state, you're putting down new gates to transform the state that act locally on the degrees of freedom. It's very rare in this system with such a large number of degrees of freedom that when you're putting down gates, that you're going to create a cancellation, that the state becomes simpler. And that was the argument then, that I will just simply, for a very long time, continue to build up the complexity. Now, the rate should be proportional to the number of degrees of freedom. Well, what's a measure of the number of degrees of freedom? Well, the entropy is actually giving you then a measure of the number of degrees of freedom that are important for our entangled state or our black hole state. But then I'm asking about the time rate of change, and so I need a scale to make up the dimensions. And what Lenny argued is that the natural scale to choose is the temperature. And so if you put those together in a conformal field theory, the entropy times the temperature, that's naturally giving you the mass. And so that agrees with the result that we're seeing. Of course, it's a posteriori, or it's not a prediction, it's a postdiction. it's there. The observation was first made about the observable, and then it was argued that complexity should behave this way. And there've actually been recently, quantitative arguments working with real quantum, they're actually random unitary circuits that actually you get this kind of behavior, or at least the linear growth. I wanted to say, though, that this is part of a much broader story where after a while, after a very long time, the complexity saturates, and that at even doubly exponential time, you might run into recurrences. My discussion today is always going to be focused on this part of the story where we're looking at this this linear growth. And I don't really have anything to say about this saturation here, although I did want to point to a relatively recent paper where these folks argued that perhaps replica wormholes have a role to play in capping off the growth of the complexity. And so I thought that was a very interesting paper, and I suggest or I recommend it to everybody. Take a look at it. Any event, that was the second. The last one on my list was the switchback effect. And so here we're going to think about our Thermofield double state, but we're going to perturb it with a number of operators here as we move along. However, the perturbations are not going to be in the usual sequential order that we think about when we're perturbing a state. Instead, we're going to have a zigzag ordering. So, T1 may be here, T2 lies to the future of that, but then T3 will lie to the past, T4 to the future. And so there's sort of this zigzag or folded time evolution. And what one finds, or what one expects, is that the complexity, well, I told you that as I evolve the system in time, I expect the complexity to grow. And so for each one of these intervals, I expect the complexity is increasing. However, there's this extra factor, this subtraction, that I also include, and I'll explain that in a moment. But the final answer then looks like the total time in this folded trajectory. But there's a subtraction every time I do a zigzag, or each time I do a fold. And for each one of those, I'm subtracting a particular amount of time known as the scrambling time. And so what is the story there? Well, let's look at T3 here. If I did not have an operator, I could evolve backwards in time, but then when I evolve forwards, I'd just be precisely canceling. I'd have an e to the plus ht to take me backwards here, and then an e to the minus ht that's pushing me forward, and those would just completely cancel, and I wouldn't get any increase in the complexity. But I didn't do that. I perturbed the state. I stuck in my favorite operator somewhere in the chain here, and so this cancellation doesn't occur. But in fact, if I have a small operator, or an operator that's, say, only acting again on a few number of the spins in my favorite spin chain, or a few number of degrees of freedom, then in fact the e to the plus ht and the e to the minus ht will in fact cancel for most of the degrees of freedom. And it takes a while for the effect of my perturbation to actually spread out and infect the entire state, or to scramble throughout the system. And so this subtraction here reflects the fact that there's a partial cancellation at each of these folds. And there's a certain amount of time, a finite amount of time, for my perturbation to spread out throughout the entire system, or for all of the degrees of freedom to know about the injection of that operator at time t3, or at any one of the folds. And so that's called the switchback effect, where I've got this partial cancellation. That's again a qualitative story about my microscopic degrees of freedom, but it's something that you can check in the geometric picture as well, where what you're doing is you're probing your black hole with shock waves. And so there's some picture here where I've got various shock waves running in my black hole throat. And I've got a very long surface that traverses all of those in my complexity equals volume picture. And it also works for complexity equals action or complexity equals space-time volume. So those are my 3 points on the checklist. Sorry, was there a question?
Yeah, hey. I have a question about the Switchback effect. So do you have an expectation about the Switchback effect when complexity is saturated? So not in the growth part.
No, I don't. I'm not sure that, we have this nice geometric picture where I have a space-time, but I'm not sure that that's really relevant. Like if I look at my simple model of my favorite space, I don't know, where's the picture? My favorite space-time here, and I push up my time slices, that volume is going to increase forever.
Yeah, sure.
And we know that something new has to happen to get it to cap off. And so these folks are saying I should start thinking about replica wormholes. You want to now probe the system with it's a great question. I just don't have an intuition or an insight into what's going to happen when I start throwing my shock waves into a black hole.
It would be interesting to see if one can use their technology to try to see.
No, it would actually be very interesting. I mean, you'd be looking at, well, actually, yeah, no, they set it up as a wave function in the JT gravity, and they're making this measurement. And you just want to, excite the system by inserting various well, you could do that with various boundary operators. No, that's a great question. Yeah, okay. In any event, this is all background. I should keep moving. Well, still some more background. We have these 3 different approaches to evaluating complexity in a holographic setting, or suggestions, proposals. A technical point that I didn't really get into is that there are ambiguities involved in defining these observables. So for example, here you can see that I introduced some scale L. Generically, what I do is I put in the curvature scale of the ADS background, but it's just saying that the dimensions here don't work out as nicely as in holographic entanglement entropy. This volume has 1 extra, or dimension 1 higher than Newton's constant. And so you need an extra length scale to make this a dimensionless quantity. And there are various similar ambiguities here. And it's always been something that we've thought about or played around, or I don't know how, actually, yeah, we have done calculations where the idea was that, well, maybe these different definitions and the ambiguities associated with them are associated with the ambiguities that I talked about at the beginning in coming up with a microscopic model of complexity. And maybe that's not a problem, but rather it's a feature of the way that this new observable complexity works. And I'm going to, well, now what we in part were motivated by that. We were also in part motivated by thinking about higher curvature theories of gravity and what the corresponding observables there would be. But I want to emphasize that everything I'm doing here is I'm thinking about Einstein gravity in the bulk. And what I just for a moment, I want to go back to thinking about complexity equals volume and what that prescription is actually doing. In particular, I want to say or point out that it involves a 2-step process. The first is that you are finding a very special surface in the bulk. And that's what maximizing this functional does. It picks out a special surface for us. And then the second step is really, though, evaluating this quantity on that surface. And then that evaluation yields the number that we're calling the complexity. And so keeping in mind that it's a two-step process, one of the things about it is that what it's doing for us is it yields this nice diffeomorphism invariant, or this nice gravitational observable in the bulk space-time, or in the gravity theory. And so what we want to do is we want to build on that, and we just want to generalize that idea. And so in general, our two-step procedure starts by thinking about codimension-one surfaces that are stretching around across the space-time here. But we're going to evaluate some functional on that surface. So there's an integral across that surface. But I've just stuck in some scalar function that's a functional of the background space-time, or the background geometry, and also the embedding function where I'm putting the surface in the space-time. So this, in a moment, you'll see, I'll give you an example where this involves, various curvatures of the space-time. It could also involve extrinsic curvatures. But what we're instructing you to do is, well, you invent your favorite functional here, and then we're going to extremize it with respect, or we're just going to extremize that functional. We're going to think about all the possible embeddings and find the surface that extremizes this particular functional. Now, having picked out our special surface, we get to choose a new function, a new scalar, and we can evaluate that on that particular surface here. And that will give me then some nice, well, as long as this again is some scalar function of the background geometry and the embedding functional, or embedding functions, that'll give me some nice observable that's diffeomorphism invariant. So that's very nice, but why should I care? Well, as holographers, we're motivated by holographic complexity. And so one of the things you can test is that, at least for a very, very broad class of these observables, in fact, what you find is that if I'm pushing the surface up in my favorite black hole space-time, that I get a linear growth, and that the proportionality constant here is in fact proportional to the mass of the black hole. And you can also think about the probes, or the tests that we did that corresponded to the switchback effect, where you're thinking about space-times with shock waves. And what you find again is that a very broad class of these observables that I'm talking about, in fact, satisfy or exhibit the switchback effect. And so what that says is that, these are actually very robust properties of a huge class of, or this very broad class of observables. And in fact, any one of them is a viable candidate for holographic complexity. Now, I want to dive into some of the details by looking at a simple example. And so I'm going to look at a case where the functional that I'm extremizing and the functional that I'm evaluating are both the same. That's an option. And I'm going to have a 1 here. That would just be, if that was it, I'd just be thinking about complexity equals volume. But I'm going to add an extra term here that's proportional to the Weyl tensor squared. And I'm thinking about Weyl tensor because in my black hole space-time, I'm looking at a vacuum equation of Einstein's equations. So R mu nu is just proportional to G mu nu, and the Ricci scalar is just a constant. And so if I added some functional that involved those, it really would just be adding a constant here. And so this is a really the first, or the simplest non-trivial scalar that I can build out of the curvatures in this context. And so I'm going to be looking at a planar black hole. And so this is the geometry. This is the blackening factor here, but as I've indicated, I've put it in Eddington-Finkelstein or infalling coordinates. And you'll see in a moment that that's a simpler way to analyze the system. And it's essentially because, my probes go into the interior of the black hole. And so that's a nice coordinate system to let me join the interior and the exterior. Not sure why I put that there, but that's just reminding you, I'm thinking about a Thermofield double state. I'm going to choose the boundary times to be equal, and I'll call them both tau equals 2. And so that's giving me this exponential with a tau or it's a whole series of exponentials with tau in my entangled state. And so we're going to be thinking about surfaces again that stretch across the Einstein-Rosen bridge, and we're going to be pushing tau up towards infinity, or pushing our surface up towards the top of the diagram. Now, if I evaluate my functional for this particular background, I get an expression that looks like this. The A here is really the 1 plus Weil tensor squared. The rest of it is really the measure factor. And I've integrated out the transverse dimensions, they're trivial, and I'm left with a radial derivative, or a derivative. Sigma is like a world volume coordinate that heads out in the radial direction. And the position in the V and the R they're functionals of this coordinate on the world volume. This is, reparametrization invariant. And so one of the things I should do is choose a clever gauge that simplifies the problem. And my gauge choice will be this one here. And you'll see in a moment, or I'll show you how that simplifies the calculations. So this piece of the measure, I'm just actually making equal to the other factors that appear in my functional. That'll be a nice thing to do. And what I'm doing is I'm trying to extremize this so I can think of this generalized complexity or this generalized volume as being an action. And this then is the Lagrangian. One of the things that we know from classical mechanics is that if I change the endpoints of my integrals here, that's going to be given by some conjugate momentum. And so this is a formula that I can pull out of a classical mechanics textbook. It's just saying that the time derivative of my action is equal to the conjugate momentum, or the time derivative of my Lagrangian with respect to t dot. Now, if I think about the boundaries, the usual Schwarzschild time and my infalling coordinate v are actually identical there. And so this becomes the momentum conjugate to v dot, or something that I'm going to be calling PV. And that's going to play a role throughout the rest of the analysis. The interesting thing about PV is that, well, there's no v dependence in my Lagrangian, and so that's actually a conserved momentum. It also turns out that if you evaluate this, you get a complicated expression, but when I make this gauge choice, and that's why I made the choice, my conserved momentum reduces down to this very simple expression involving an r dot and a v dot. Now, given my gauge fixing and my conserved momentum, it turns out that's enough to solve for my surfaces. And in particular, the radial profile is determined by a classical mechanics problem. And so if I massage these two equations, I end up with the following equation, where I've got a kinetic energy, a potential energy, and then an energy given by PV squared. And the effective potential takes this form here, where I've got various factors from the measure and this blackening factor from the geometry. And there's an overall sign. But what does that look like? Well, I get pictures that look like this. So here's my effective potential versus R. And so given these various factors, I get something that for very large R is large and negative. It hits 0 when I get to the horizon. It comes up to some maximum here, dips down for a while, but then because of the A factor or A squared in the effective potential, it takes off to infinity again here. Just to compare what I would have gotten if lambda was equal to 0, I just get a profile like this where I get the maximum and then it dips down and just goes to 0 again. Now, what I'm going to be doing is I'm going to be studying this problem and I'm going to be looking at interesting trajectories. And so what I do is I pick an energy here. The trajectory starts at the asymptotic boundary. So it starts at very large R. It'll come in traversing the potential, and then it'll hit the potential at some point and it'll bounce out again, going out to large R. And what that means, well, we'll see pictures in a moment. It's heading out to the other asymptotic boundary. So if I start down here at PV equals 0, it just comes into the horizon and goes out again. That's just, you know, the T equals 0 slice where it cuts through. There's some interesting ones here where I bounce off the outside. But then the most interesting one is where I approach the maximum here. And so it'll take an infinite amount of time or world sheet or whatever, world volume time to reach that and before I bounce out again. And so that's a very special point, and it has a very special value of the momentum that I'm calling P infinity. And the radius of that maximum gets a special name. It's this R sub F. And I guess one of the things I did not say is the minimum radius here, the turning point, that's the point where R dot is 0. And so that's determined by this equation where I'm just equating the energy to the effective potential. Another point that arises or that comes out of that is that this P infinity, it's straightforward to show that it's actually proportional to the mass. And that'll play a role, of course, later on. So here are some of those pictures. With P equals 0, I came across, straight across, I hit the bifurcation surface and then I keep on heading out. If I look, or one of the things I have to do though, is I have to figure out, I'm giving you the profile R, but I have to figure out where I connect on the boundary. And so I have to do some integral here that comes from the gauge fixing condition. And if I evaluate this for different values of P, what I find is a graph that looks like this. So it actually starts at 0 at P equals 0, and then it comes up, there's a pole here, and then it comes back down on this blue branch and heads out, or comes back down as PV heads off to infinity. And so on the red branch, what I'm doing is I'm actually pushing up and I'm getting slices very much like the extremal volume slices that stretch across here. And what happens as I hit the pole, or the pole is right at P infinity, I'm getting a surface that really hugs along R equals RF, this special value, for a very, very long time before it heads out to the asymptotic boundaries again. On the blue branch, I find another set of surfaces, but these are actually crossing over, I've inverted the colors here. The red branch were these surfaces that were bouncing off the outside of the potential. The blue branch, you're actually crossing the peak or RF, and you're hitting the potential where it's rising closer to the singularity or closer to R equals 0, but you get a whole new set of surfaces with they meet the boundary at the same times, but they have a different profile. They probe closer to the singularity. An interesting point is that if you go way out there, that the tau actually starts taking negative values. And because of a reflection symmetry, tau goes, or t goes to minus t in this problem, there are actually, there's a corresponding surface up here that has this profile, but it's time reflected. And so it looks like this. The reason you didn't see this, or we didn't see this surface in our coordinate system, is that the v coordinates only, or they didn't let me go down into this part, the white hole part of the space-time. And so we were inferring this indirectly. But what that means is that for a given boundary time, I can have up to 3 extremal surfaces. The question is, which has the maximal volume? And it turns out the global maximum are these simplest ones, the ones that corresponded to bouncing off the outside of the potential. As I said, or as you go towards tau equals infinity, you're riding up here, you're very close to the pole. And so the first order, or actually to leading order, the time rate of change is just given by p infinity, which in turn is proportional to the mass. And so you're getting a time rate of growth that's proportional to the mass. In fact, that's true on either branch. I could also, follow these blue line, or the blue branch, approach p infinity from above. I'd get the same growth. You can also look at the switchback effect. Here, the thing that you should worry about is, are there delta function contributions at the shock waves? It turns out the answer is no. And so you're getting the expected switchback effect as well. Oh dear. One of the comments is that I was a little bit glib in that I didn't talk about the particular value of lambda that I chose in the pictures that I drew. And in fact, lambda can't be too large, or you can't get too far from 0. There's a range. If you go beyond that range, in fact, you lose this maximum, and you don't get the same kind of behavior. You don't get the pole in PV as you scan across in that other graph I was showing. An interesting point is that even though these are the maximal volume surfaces, there are these other saddle points, these other extremal surfaces, and one might ask, do they play a role when we understand the full picture of complexity equals, or holographic complexity? An interesting point about them is that they're probing the region closer to the singularity than these surfaces that are the maximal, or the maximal complexity surfaces. I'm running out of time, but I'll talk a little bit about what would the analog of complexity equals action, or complexity equals volume 2.0 be? Remember there, I was picking a region of space-time, namely the Wheeler-DeWitt patch, and then I was evaluating either the action or the space-time volume of that region. In both cases, again, we were producing some interesting diffeomorphism invariant observable in the bulk. And even though there's no extremization procedure, I will say that the observable consists of 2 elements, or defining the observable consists of 2 elements. First, you're picking out an interesting region of space-time, and you're doing that by choosing the bounding, or the surfaces that bound that region. In this case, they're just null sheets. And then the thing that you're doing, which is different in these two, is that you're evaluating some interesting geometric feature of that region. And for the complexity equals action, you're also evaluating terms on the bounding surfaces. And so it's, given our experience with the previous generalization of complexity equals volume, we go through a similar construction, where we have our time slices in the boundary. We're going to think about two surfaces that connect those boundary time slices, well, a top and a bottom, and they're bounding some region of the space-time in the interior. And so I'm going to define some functional that, some nice diffeomorphism invariant functional that lives or that gets defined on that geometry, and it'll involve a scalar evaluated on the top surface, scalar evaluated on the bottom, and a scalar for this region between the two surfaces. And what I'm going to do is I'm going to think about extremizing that functional with respect to the positions of the top and the bottom surfaces. And that will define for me then my space-time region in a nice diffeomorphism invariant way. Of course, once I've given that region, I can evaluate lots of interesting quantities on those surfaces and the interior region to produce my new observable. Again, the question is, so what? Well, in many cases, and this is a work in progress, we recover again the linear growth and the switchback effect. So again, these observables as well seem to be interesting candidates for holographic complexity. So in this case, again, very quickly, a simple example. I'm going to, my functional is the volume of the top surface, the volume of the bottom surface, and the space-time volume in between. I've chosen, I have to have a relative coefficient between these different quantities, and I've just done that by introducing these constants alpha plus and alpha minus in these two functionals here, boundary functionals. And what you can do is you can extremize this quantity, and this is something that various authors have looked at, in particular at the ADS celebration a number of years ago in Princeton. Witten gave a talk where he wasn't doing exactly this, but he discussed how the extremization would go. And what it produces are very nice surfaces called constant mean curvature, because what they satisfy is a nice equation like this. The trace of the extrinsic curvature is equal to some constant. Remember that when I'm evaluating complexity equals volume, in the background, I'm getting exactly this equation, but it's the trace of the extrinsic curvature equals 0. Here with this setup, you're getting two different surfaces where the trace is equal to a constant. And the plus and the minus just means that one of them bends up and the other one bends down. Now, in the limit where those constants are going to 0, in fact, it pushes the top surface up as high as it can go and the bottom surface down as far as it can go. And so what happens is that region or those surfaces become null sheets or approach null sheets as best they can. And then the region that I'm defining there is precisely the Wheeler-DeWitt patch. And so if my functional that I would like to evaluate is in fact this one, the alphas are going to 0. And so what I'm doing is I'm evaluating the space-time volume of the Wheeler-DeWitt patch. And that's nothing other than the complexity equals volumes 2.0 prescription. Alternatively, I can choose another functional to evaluate, and I could choose the action, including the various boundary terms. And then this becomes the complexity equals action proposal. Just as a side comment, you could also use this prescription where I've pushed my C plot or my sigma plus, the top surface, up to the singularity. And the functional that I could evaluate could just be functionals on that surface. And that would be an effective way of probing the space-time singularity. Now, that brings me to my conclusions. And I'll just say that, what we've done is, extended the usual prescriptions for holographic entanglement entropy to get this rich structure of gravitational observables. Many of them seem to satisfy, these features that we're looking for in complexity, namely the linear time growth and the switchback effect. And so we have a very broad class of holographic observables now that all seem to be equally viable candidates for holographic complexity. If you'll indulge me, I have a few more slides, or I could just open it up for questions here. So I leave it to Hugo to tell me, can I do a few more slides or?
Yes, of course. Please go ahead.
Okay. So I'm going to focus on one of the points that appears here, which is this idea about couplings. And it was really motivated by the question, that I'm sure Mikhail is ready to ask me, that is, how do I really connect the ambiguities in the field theory or in the microscopic model to the ambiguities in the gravity theory? And I'm not going to have an answer for you, Mikhail, but I was led to this some interesting observations, which is that, well, one of the curious things is that my parameters can't become too large, or it seems that they can't become too large. In particular, I gave you this range here, and that's what gave me a nice effective potential that had a nice maximum, and this whole story that I told you. Now, what happens if I go, say, beyond this critical value? What if I make it a little bit bigger? Well, at the critical value, in fact, my maximum becomes a inflection point, and then beyond that, I just don't have a maximum. But I can do the same analysis. In particular, I can ask, what is the boundary time associated with various extremal surfaces? And what I find is that rather than a pole here at a special value of this conserved momentum, what I find is that there's a maximum still. And depending, where I am in my parameter space, that maximum can be small or large. In fact, if I'm very close to the critical value, it can become, very, very large. And what that means is that I have these extremal surfaces extending out to some very large time. And so the picture that I would draw is actually taking that same picture and putting it sideways. This is the boundary time now. And this is my conserved momentum. But remember, the conserved momentum is giving me the time rate of change of my observable. And so what I see is that, the time rate of change grows, and then I'm getting a constant or linear growth for a very long time, which was, desired. But then, beyond that, I don't have an extremal surface anymore. And so I'm not exactly sure what I should be doing there. And so I'll just leave it with, that seems strange. But I encourage you, after the recording is off, to ask me what other thoughts I might have on that. I'll just leave it right now by saying that there seems to be lots to explore with these new gravitational observables and with holographic complexity more generally. And so with that, I'll thank you for your attention and open it up to questions.
Thank you, Rob, for the very nice and very clear talk. indeed, we have some questions, I think. Oh, we already have some people asking.
Okay.
Elise,
yeah, go ahead.
Hi, Rob. Thank you for a very nice talk. I have a question about one of the let's say, parameters in the boundary theory, which is, I think, more important than the others, and this is the tolerance parameter. Because as you very well know, the fact that the complexity saturates means that you keep that a finite number. It can be small, but you don't allow it to go to zero. Because if you allow it to go to zero, your saturation value goes to infinity. So what do you believe could be in the bulk the equivalent to that epsilon tolerance parameter?
Yeah, in fact, I would take a different tack on it. And I mean, there are, I know you've seen me give talks about sort of microscopic models of how I might define complexity in a field theory. And you define these operators that are sort of path ordered Hamiltonians or exponential of a Hamiltonian that act on my state, and my gates become operators that I allow in my control Hamiltonian. The thing is that in that case, the parameters that I'm using in the way that we were doing it anyway are real parameters. So my control functions are arbitrary numbers, and effectively what that means is I have fractional gates. Whereas in the discrete model that I talked about before, the gate did some simple operation, and it was a discrete operation. So for example, if it was a phase shift, it would have been a very particular phase shift that I did, say pi by 2 of the phase of a particular qubit. But now I'm allowing for arbitrary phases, and that's just an example. But the idea is that because I'm allowing these real parameters or fractional gates, at least in the models we look at, you can always get to the state that you want very exactly. And so the tolerance actually, well, you don't need a tolerance in that case. You can let the tolerance go to 0, and you can still reach the state. But I'm changing the model a little bit from what the quantum information folks think about usually. In my context, I'm setting it up in a way that I can do operations sort of with a real parameter rather than just laying down a discrete gate.
Okay, but that's on the boundary. But
right.
What in the bulk? Let's say I do have an epsilon. Let's say we do.
If you did have an epsilon, right?
What is it in the bulk? You have many, because you allow even many. You have a large class of candidates, but what would be the reflection of epsilon in them?
Yeah, well, again, I'm going to push back again, because that was always a puzzle for me, because, one of the things that the discrete systems, one of the things you see is that the complexity landscape is very, it's extremely rough. Like states that seem nearby by common sense, perhaps, are actually have very different complexities, because, with my discrete operations, for example, I can step right to, with one step, I might be getting to a particular state. But then if I change the phases a little bit, I may be stepping around all over the place before I can land close to that one. And that roughness, I mean, that was a puzzle to me, because in the geometric setup, you know, with the observables we're playing with, you don't have any indication of that. Like if I make perturbations of my geometry, like we talked about shock waves, but if I throw in, you know, some gravitational waves or whatever your favorite scalar or whatever field, you know, those are small perturbations of the state. And correspondingly, they make small changes in my gravitational observable. And so that's why I zoned in on this idea that I think the complexity model is really, you know, probably closer to the ones that I talked about or that we built for the field theory, where you have, you know, real parameters, and it's not a theory of discrete gates. Exactly. I mean, the discrete gates, that system is something that lets us build a lot of intuition. But I think ultimately it has, you know, shortcomings like this roughness and maybe the epsilon that aren't reflected in what we see in the gravitational framework.
Okay, so you would not expect it to, your answer is maybe semi-classical gravity doesn't contain epsilon.
That's right, yeah.
Okay, thank you.
Okay.
I see that Nishan also has a question.
Yeah, thank you for the talk, Rob. I had a question regarding the one of the proposals for complexity, which was the complexity equals volume 2.0.
Okay.
I understand complexity from a quantum information theory perspective, and an important step in evaluating complexity in that case is an optimization procedure, which is there in the complexity equals action as well as the complexity equals volume proposals. But I don't see the same thing in the complexity equals volume 2.0 proposal.
Yeah, I think, oh, sorry, go ahead.
If I understand the reason why you still think this is interesting is because it still shows the linear time growth as well as the switchback effect, which you've been using as a marker to see if they match with the proposals, right? Is there anything new that we can learn from evaluating things on these codimension-zero patches? Yeah, that was my question.
Yeah, I guess I am. When you talk about the optimization, I think you're thinking of, like, when I think about complexity equals volume, I see that I'm maximizing. I have a functional, and I'm optimizing it. I'm maximizing, you know, the space-time volume. And it was a comment that I made here that when I turn to these codimension-zero and I'm talking about the Wheeler-DeWitt patch, it's not obvious, you know, that there's an optimization. And it's more that I just picked my favorite region of space-time. But the way I set the problem up, well, I called it here, find a special bounding surfaces, but the way I set it up, I'm really am optimizing something, or I'm doing an analogous procedure where I'm extremizing some functional. And then what I argued here is that these observables, in particular, complexity equals volumes 2.0, that's actually it's sort of a limit, you know, a singular limit, perhaps. I don't know if I want to use that word, but it's a very special limit of a family of these optimizations. And so I think it fits naturally in that framework that you're talking about. Although it sits maybe at the boundary of the space with this sort of very special limit that we're taking.
As a limit of this, I think it fits in very well with that definition. Yes. Yeah. Thank you.
Yeah.
Let's say that we take another. Oh, okay. Elisir, please go ahead. Let's say that this is the last on the record question, and then afterwards we can stop recording and move to a more informal discussion, if that's okay.
I forgot to lower my hand. So
Oh,
Okay,
Can I ask a question?
sure, go ahead. Hi.
Hey, Rob. Thanks for the nice talk. I want to ask you about this lambda. So it looks to me that when you put some critical value for this lambda, it reminds me of the swampland things. So it looks like if your lambda is too big, then it seems like this setup is in the swampland of something. So maybe the holographic conjecture of complexity, like, yeah, that's, I don't know if you have more comments on this, or is that what you are thinking at the moment?
You know, that's what I was thinking until I prepared for this talk. And I don't really think that's the case. I think it's just something that has to be better understood. But I'm not going to make any comments on the record.
Okay, let's hear your comments after the record.
Okay.
okay.
Thanks.
In that case, let's thank Rob again for this great talk. And let me now stop the recording.